The topics of our today's discussions are parallel axis theorem for an area and moment of inertia for composite areas. As such, we are going to have really two main objectives. The first one is to apply the parallel axis theorem to solving some of the problems. The second one is to determine the moment of inertia for a composite area. As such, there are certain activities associated with our discussion. They're listed here. This is very similar to previous lectures. We are going to concentrate on, again, parallel axis theorem and methods for determining parallel axis theorem for the composite areas. We're going to have reading quiz, applications, the concept quiz. There's a group problem solving and attention quiz to pretty much wrap our session up. So let's start with a reading quiz. I assume you guys read the appropriate chapters under the topic from the book. Number one, the parallel axis theorem for an area is applied between, there are four choices here, A, B, C, and D. You would like to pick the best choice, an axis passing through its centroid and any corresponding parallel axis, any two parallel axes, two horizontal axes only, and two vertical axes only. So among these four choices, the best one seems to be A. The parallel axis theorem for an area is applied between an axis passing through its centroid and any corresponding parallel axis. If the axis is not parallel, then we won't be able to apply this theorem. The second quiz is the moment of inertia of a composite area equals to blank of the moment of inertia of all its parts. Again, let me read it to you. The moment of inertia of a composite area equals to the blank of MOI, or moment of inertia of all of its parts. And the correct answer, you probably have guessed it, is going to be B, an algebraic sum. We want to make sure that we consider all the signs. If it is plus, it's going to be an addition. If it's minus, it's going to be a subtraction. So the moment of inertia for a composite area equals to the algebraic sum of moment of inertia of all of its parts. We're going to do a few examples and things would become much more clear. So what are some of the applications? Why do we need to know about moment of inertia? Here's an example. This is a cross-section of a T made of two pieces of wood. The cross-sectional areas of structural members are usually made of simple shapes or combination of simple shapes. And to design these types of members, we need to find the moment of inertia. Otherwise, we are going to run into problems of buckling. We're going to run into the problems of other types of premature failures that could be associated with a poor design and poor calculation of moment of inertia. It is also much more useful to pretty much, if you can do a simpler method of determining the moment of inertia. Again, we are going to take a look at some of those, and you can pretty much read this on your own. So more applications. Think of having a composite cross area as such, and this is a built-up beam or member. Is used in different types of structures, including building construction. And for example, we would like to find out what will be the moment of inertia of this axis. We actually put that right there. This is the centroid, and it's very important to be able to calculate the moment of inertia of each individual section, and at the end we need to find the moment of inertia with respect to the axis that's shown here using the parallel axis theorem. Of course, this is a straight line, not a sinusoidal wave, so make sure you guys don't repeat what I did here. So there are much application of moment of area calculation in design, and one cannot really perform design not knowing one of the basic properties of the section, which is the moment of inertia. So, what is a parallel axis theorem for an area? Here is a generic version that involves more math and physics than anything else. This theorem relates to the moment of inertia of an area about an axis passing through the area's centroid. So, in order to determine the MOI, or moment of inertia, of the area about a corresponding parallel axis, not just the centroid, but having another axis, then we need to use this parallel axis theorem. It has much practical applications, especially for composite areas. So now let's assume that we have an area, arbitrary area. It has a centroid C as shown here. This area is shown in blue actually here, and the x prime and y prime axis, it is actually passing through the centroid of this area. So if the centroid of the area is C, x prime and y prime, the Cartesian coordinate system, they actually pass through the centroid. So if we want to find the moment of inertia about the x-axis, not the x prime axis, but the x-axis, another axis that is shown down here. This is the beginning of x, this is the beginning of y-axis. If we want to find the moment of inertia of this area with respect to another coordinate system that must be parallel to x prime, y prime, we call it xy. Remember, there are certain conditions here, and that those conditions must be met. Otherwise, this theorem cannot be applied. One of that is the axis must be parallel. And so Cx prime must be parallel to Ox, and Oy must be parallel to Cy prime if we would like to find the moment of inertia about the other axis. So the distance d sub y is the distance that the new axis, the parallel axis, is away from the old axis, which was the one that's passing through the centroid. And also the y prime axis is away by a distance d sub x from its parallel corresponding axis, which is y. So these conditions, they must met. If we meet those conditions, then we can see that we can use the parallel axis theorem. Now, what this theorem says is we cannot really use this theorem without finding what would be the moment of inertia about the centroid first. So I sub x here, and really what it would do is it's going to find the area over the integration would be over the entire area of y squared dA. dA is that small area that we use for integration. Remember, in integration, we're actually taking the integral for this small little element dA, and we take it. We take that integral over the area. So in this case, if you want to do that, in this case, the y here would be y prime plus d sub y, right? So if you want to take the moment of inertia of dA with respect to another axis, considering the applied equation, then we need to substitute for y in terms of what y is in this case. Y in this case is the distance of the dA, the small differential element, from the x-axis, the new axis, okay, right here. So y prime was the distance of the differential element dA from cx prime. But now y, the new y, which includes y prime plus dy, would be that new distance. Now remember, d sub y is the distance between these two axes, cx prime and ox. So as such, we do a substitution. Instead of y, we would put y prime plus d sub y. There's a square here. We keep that. We carry the integration on. And as such, you can see there are three terms here. Using the first term is what? As you can see, the first term is relates to the definition of the centroid, isn't it? So the definition of the centroid is y prime bar is integrating over the area y prime dA. This is the differential element. We divide that by the integral over the entire area of dA, which is the differential element. Okay, and then we know that in this case, because C is the origin of the x prime y prime axis, the axis that actually passes through C, then y prime bar is 0, right? Because we're taking the moment of inertia of that axis with respect to its centroid. As such, y prime bar would be 0. And again, we do a substitution here. One of them was going to drop out to 0, right? So we're going to end up with the summation of, we're going to have AD squared. Okay, so this one is going to, if you have your y bar prime as 0, then the y prime dA would be 0, right? So this is going to be 0, right? So if this is 0, then this is going to drop into 0, right? So this is going to be 0. If your y prime bar is 0, then integration over the entire area of y prime dA, which is the differential element, that would be 0. If that is 0, that means the purple term here in the purple box, that would be 0. So we end up with two terms. One is the first one and the last one. They're both shown in kind of like a blue-green color here. And we can simply do ix prime plus a d sub y squared, which is nothing but when you take the when you integrate the differential element over the area, that would give you a, right? So this is a, and then it's going to be a d sub y squared, right? And then the first term, which was integration over the entire area of y prime squared dA. Again, dA is the differential element here. In that case, then that would be ix prime, isn't it? If you compare this term here in this box with the term right above it, you would see that if this is called I sub x, moment of inertia with respect to x, then down here, again I'm showing with a little arrow, that would be ix prime, wouldn't it? Right? So this is really the parallel axis theorem. Every time we would like to take the moment of inertia of an area with respect to another axis that is parallel to its axis that passes through the centroid of an object, we are going to use this parallel axis theorem. Ix prime is nothing but the centroid of an object with respect to its the moment of inertia of an object with respect to its centroid, and a dy squared is nothing but squaring the distance between the two axes, multiplying it by the area. Okay, so this is really the bulk of parallel axis theorem. Okay, we can do the same thing, of course, for moment of inertia with respect to y-axis, and also for polar moment of inertia and other types. We can pretty much look at those in the form of examples, but the bulk of it here is that this is the parallel axis theorem, and we want to make sure we understand all these terms. So here's an example of a composite area made by adding or subtracting a series of simple shaped areas. These areas are rectangles, they're triangles, they could be really circles, semicircles, anything that is defined within the mostly used shapes. So, for example, the area to the left can be made of the entire object minus the hollow part, which is shown by white, or it could be made up of individual pieces shown in blue. This could be 1, this could be 2. The entire cross section is much easier. Instead of dividing it into 4 and add those up, it would be easier if we assume 1 for the entire rectangle that I'm encircling in red. So first we take the moment of inertia of that one, then we would subtract the moment of inertia of the hollow part that's inside, right? And to that we're going to add this one and that one. Or we can do half of this, because this is a the cross section is symmetric. We can just do half of that. So let's look at some of the steps. We divide the areas. We would locate the centroid of each part, and we are going to use the parallel axis theorem, and we would then calculate the entire area, the moment of inertia of the entire area by the reference axis, by forming an algebraic summation of the all these individual areas. And then if we're supposed to subtract, we would subtract depending on the shape of our cross-sectional area. The shape of our area, in this case, there's a hollow circle, so we would simply subtract that from that entire area in order to go from here to here. Okay. Okay. Here's an example. This is a given cross-sectional area similar to one of the problems that you would solve. The moment of inertia of the area about the y-axis and the radius of gyration in case of y is given. We would follow the steps for the analysis that I just described. So we're going to divide this into 3 areas shown here as 1, 2, 3. And the solution here is that the solution strategy is here that the centroids of these 3 rectangles are in their center, as you can see, and we find the using the parallel axis theorem, you would want to find the centroid of this object with respect to the new centroid, which is the centroid of the composite object. So let me go back to step number 2. The centroids of these 3 rectangles are in their center. The distances from these centers to the y-axis are 0, 1.5, and 1.5 respectively. This is the distances that are given here. Okay. So from the inside back cover of the book, you can look up the moment of inertia of a rectangle about its centroid. It's 1/12 of bh cubed. Make sure you guys don't get confused between b and h. That's one source of error in solving problems, is to confuse B and H. Depending on the layout of the section, B and H would be different. For example, for section number 1, which is the bigger block that rests on top of the other 2 blocks, B is 2 inches and H is 6 inches. Although if you want to go by common wisdom, it could be that you think H would be the height and B would be the width. But because of the layout, B and H is different here. So we want to make sure you understand this part of this, okay? Very important. We lay the block flat on its longitudinal side rather than the transverse side. So we want to make sure we understand that. Then there's a 36 inch to the power 4. That's really would be your I sub y. So we calculate that. Then for 2 and 3, they're the same, they're equal because of the symmetry that exists in this shape. It's symmetrical. So we take Iy prime and then we add a d sub x squared to that, and that is the distance between the new axis and the centroid of each of these little individual blocks. So now I sub y would be I sub y1, I sub y2, I sub y3. We just add I sub y1, 2, and 3 together. We take the summation. 54.7 would be the I sub y. Now we're going to use some properties of radius of gyration where we can calculate that. A would be 6 times 12 times 4 plus 4, 20 inches. We're going to do a substitution in I sub y that we calculate from up here. Remember, I'm allowed to do this kind of arrows because I am trying to provide you with how to do this. But you guys are not allowed to do this when you submit your homework. Don't do that, because this is part of your learning, but that is part of you guys presenting what you've learned. So it's very different. So I'm allowed to do that. One of you guys said, well, during your lectures, I've seen you really have arrows all over the place. I thought I'm allowed to do that in my homework too. Well, I'm sorry, but that doesn't fly with me because we're just talking about, we're comparing 2 very different things. Anyway, so 54.7 divided by 20 here, which is the area, and then that will be the case of y as 1.65 inches. Okay. So let's take a look at a concept quiz here. You can read it to pretty much get warmed up a little bit. For the area A, we know the centroid C location. This is an area. The area is like an oval. We know the centroid. We know the centroid's location, area, distances between the 4 parallel axes, and the moment of inertia about axis 1. We can determine the moment of inertia about axis 2 by applying the parallel axis theorem. Again, this is a little bit tricky, but they're excellent questions for the short exams or quizzes. So we have 4 axes here, 1, 2, 3, and 4. One of them, number 3, goes through the centroid. What we try to do is, we already know the location of centroid here, which is this point. We also know everything else about this object with respect to axis 1. But what we want to do is we would like to find the moment of inertia about axis 2 by applying parallel axis theorem. could that be possible? Which would be the correct answer here? Directly between axis 1 and 2, between axis 1 and 3, and then between 3 and 2. That's another option. C, between axis 1 and 4, and then axis 4 and 2. None of the above. So let's read the problem again. For the area A, we know the centroid's location, area, distances between the 4 parallel axes, and the moment of inertia about axis 1. So this is known, right? We know moment of inertia about axis 1. We can determine the moment of inertia about axis 2, okay, by applying the parallel axis theorem. Can we go straight from applying it from 1 to 2? We can't do that because the parallel axis theorem applies to, first we need to know the moment of inertia about its axis 3. Otherwise we won't be able to do that. So we can't do this one. We can't really do option C and D. The correct answer is really B, because first we need to apply the parallel axis theorem between 1 and 3, since 3 runs through the centroid of this object. After that, we can then find the moment of inertia of this cross-section with respect to any axis that's parallel to the axis that goes through its centroid. So that's really the bottom line. The second conceptual quiz. These are very neat and conceptual quizzes. If you understand them, that means you really understood the concept. So let's take a look at the same object. This time, area A, 4 axes, 4 axes, 1, 2, 3, and 4. Then the distances between 1 and 2 is d sub 1. The 2 and 3 is d sub 2, and 3 and 4 is d sub 3. C is the centroid. For the same case, consider the moment of inertia about each of the 4 axes, okay? About which axis will the moment of inertia be the smallest number? Very interesting. The question would be the smallest about axis 1, 2, 4, or 3. Right off the bat, I'd say C. And the reason for that is if we want to determine the moment of inertia of A with respect to any other axis that does not go through the centroid, then we need to use the parallel axis theorem according to all these parallel axes that are given here, okay? So if we want to find the moment of inertia about A with respect to any other of these 1, 2, or 4, then we would add some quantity to that. So the smallest value would be the centroid with respect to the moment of inertia of the axis with respect to an axis that goes through the centroid of the area. Okay, let's take a look at a group problem solving, and then we would do an attention quiz, and we would wrap the session up. So the shaded area is shown in the figure. It shows in blue the moment of inertia for the area about the x-axis and the radius of gyration in case of x is what we would like to determine. We are going to follow the steps that we discussed. We are going to divide it into 3 areas, 1 triangle, 1 rectangle, 1 circle, and then we would do our calculation. The given area can be obtained by subtracting the circle from the sum of the other 2, triangle and the rectangle, and then information about the centroid of a simple shape can be obtained again from the back of your book, inside cover of your book. The perpendicular distances of the centroids from the x-axis are given here, d sub A, d sub B, and d sub C respectively. So we are going to use I sub x A, that's for section for shape A, which is a triangle. And then for section, this is all for A. And then we would also use the area of the triangle itself here. And we would use that one. So I sub xb, the same thing. Well, similar procedure, but not the same. I sub xc, it's for that circle, so we need to also find that out. So what we did here was really, we would like to find the centroid of the object first, and then we could determine the moment of inertia. For the entire object, the moment of inertia would be 799.8. Now, from this point on, we need to apply the what we did here in this case. I'm sorry that this is a little bit confusing here because of all the. Okay, so what we did in this case, we did that, but except at this time we did it individually. So I sub XA, we calculated for A with respect to another axis, which is not the same as it is for its own. We have it, okay? So this is the I sub X for the triangle, that's portion A, and then this is the parallel axis theorem. First, it's the area, and then this is the D, okay? Now this D is only for area A. The same thing here. This is D for area B. Okay. And this is D for C. So instead of finding the summation of all of the moment of inertias and then use the parallel axis theorem, here we demonstrate that that could also be done individually, and then we would follow all summation rules according to the algebraic sign that you would see here, either plus or minus. And then from that point on, from there on, k sub x could easily be calculated using the appropriate equations. Let's take a look at an attention quiz before we wrap this session up. Let me look at, well, I can look at both of them, but let me look at both of them. Okay, let me look at number one. For the given area, the moment of inertia about axis 1 is 200 centimeter to the power 4. Okay, so what is the moment of inertia about axis 3? So we know the axis 1 moment of inertia about axis 1 is 200 centimeter to the power 4, and then we would like to find what would be the moment of inertia about axis 3 in this case. So what would you guys use in this case, and what would be the right answer? Well, you're going to use the parallel axis theorem. The area is given. It's important to realize that this is given with respect to axis 1. That's the 200 centimeter to the power 4. We need to set up the equation, and knowing we're going to use the A D square plus what we already know, the 200 about axis 1. Okay, so So here we need to work backwards, because from here we want to know the moment of inertia about axis. This would be I sub with respect to 3. Okay. Is that right? Yeah. The I sub 3 here. No, I said it the other way around. This is 200 with respect to axis 1. 200. You guys follow me here? 200 is I sub with respect to 3, which is the centroid, plus a d squared. So this is not really correct. Yeah, just cross this top part out. Again, I'm allowed to do this, but you guys are not when you submit your assignments and homework. So be careful, you guys, with providing it really neat way. So here, 200 would be I sub 3 plus AD squared, as A is given, and D is actually given. It's in this case, D would be the distance between 1 and 3, so it would be 2 plus 2, 4. So this is 4. So we square that'd be 16. So 16, that'd be 160. It will be 200 minus 160. So the correct answer here is really D. Okay, but this is the equation. 200 is I sub 3 plus a d square, and this d is 4. This is number 4. So this is the correct answer. The second attention clue is the moment of inertia of the rectangle about the x-axis equals to what? A is 8 centimeter, 8 unit. B is 56 unit. C is 24, and D is 26. Again, this is about the x-axis. So we're going to use the parallel axis theorem. For this is going to be B h cubed. Okay. And then we would use that plus AD squared. Okay. Okay. So if you do the calculations, the answer is going to be 56 centimeter unit. So that pretty much brings me to the end of our today's discussion on moment of inertias. This is the end of the lecture. Let learning continue. If you have any questions, feel free to contact me. Thank you.